All right, in this video I'm going to be talking about absolute extrema for a function of two variables. And before we go into that, I want to kind of call back to, what we did with this last year. And, say we had a function, kind of the extreme value theorem was what guided us here. And actually it's the same guiding principle. Was that if you've got a continuous function on a closed interval, meaning we're going to include this point and that point, it's got to take a maximum and a minimum value. Has to. Okay. Here was the maximum. That looks like the minimum. And the way we actually went through and solved these problems was we located all of the critical points. We found the value of the function of the critical points. We evaluated the endpoints as well. Okay. And that was because this was the domain, right? It was an interval along the real line. It was a closed interval. But if this was, say, a surface in space, I would need something more like, a region in the plane. It's actually a pretty good drawing. Maybe. Did that kind of, I don't know, maybe it looked like there was snow in the mountains, but the idea is that we're going to have some sort of, instead of a closed interval, we're going to have a closed region in the plane. And we want to maximize a two-variable function over that region. Now, it won't just be quite as easy as plugging in two numbers, the two endpoints. But the concept is exactly the same. Okay, so pretty much what I'm going to do is I'm going to assume that you were good enough at this last year that you made it on to me this year, and that also you could just pick this up by watching me do an example. So I'm going to work a pretty good, solid example. I think either the maximum is going to be on the boundary, or the minimum is going to be on the boundary, and the maximum is going to be in the interior, or something like that. Found a good one. I'll say that I did pull this one from the textbook, so there is a chance that I did also assign this as a practice problem. If that's the case, well then I guess at least you'll know how to do it. So, for example, let's see. Oh, I gotta find it now. Yes, f of x and y is 3x squared. We said 3x squared, I've already forgotten, plus 2y squared minus 4y. Okay. And I am interested in maximizing and I suppose minimizing on the region, and I think it's just going to be easier for me to draw it for you. Okay, so we're going to maximize this function over the region R as I've drawn it. Okay, notice that the boundary of R is comprised of the curve y equals x squared and y equals 4. And for y equals x squared, x is specifically between -2 and 2. And that's going to be relevant for us later. Okay, so we're going to find maxima, the absolute maximum and the absolute minimum for this function over that region. Okay. I think that, in the textbook or in a lot of videos, they would start off with a region that was, say, rectangular, but what'll end up happening is you just end up plugging in constant values for x and y, and then you end up with a problem like this. You're like, hey, what do I do with this? And so I'm just going to jump straight to this and trust that you could do the easier one after watching the more difficult one. So what I'm going to need is I'm going to need a list of our critical points, right? So that involves getting the gradient, or just getting all the partials written down. So fx is equal to 6x, or just 6x. And fy is going to be, what is fy? That'll be 4y minus 4. Okay, so places where I'm only seeing one critical point, right? Because this is always defined everywhere, right? There's not any x's and y's that I could put in that would make this undefined. So the place where it would be the 0 vector would be where 6x is equal to 0 and 4y minus 4 is equal to 0, which to me is saying that x needs to be 0 and y needs to be 1. Okay? So critical points are just going to be at 0 and 1. Okay. I'm not even going to go through the whole second partials test to find out whether this is a relative maximum or relative minimum, because I don't care, right? What we did, sometimes in AP calculus, we could save a little bit of time. If we could tell that something was a relative minimum and we were trying to find an absolute maximum, we would not evaluate the function at that relative minimum. But for this one, I just don't care. I'm just going to run. It would be faster for me to run 0, 1 through this function than it would to run the whole second partial analysis, especially when I'm interested in finding the maximum and the minimum anyway. So I'm going to say, well, f of 0, 1 is going to be equal to 0, 2, minus 4 is negative 2. Okay, and so I'll kind of have that, in my list of candidates right there. That's all the critical points for the whole function. So now I need to check the boundary, check basically the endpoints. But for now, the endpoints are going to be this curve. And actually, no, hold on, I got ahead of myself. I'm going to start with y equals 4. Because that's what would typically happen. You'd look at a rectangular region or a triangular region with one where one of the variables was constant, and you would just plug in on it and see what's going on with that. So I think I'll start with that one, and I'll use purple. Okay, so I'm considering, the boundary where y is equal to 4 and x is between negative 2 and 2. So now what I have is I'm interested in f of x and 4. And so that'll be 3x squared plus 2 times 16 is going to be 32. Minus 16 would be plus 16. And then what I'm going to do is I'm going to find the absolute maximum and minimum of this function on that restricted domain. Which shouldn't be too hard because this thing has got a whole bunch of symmetry to it. Its minimum is going to happen at x equals 0. Like these are just things you know about the parabola of 3x squared plus 16. Its minimum happens at 0, which is going to be 16. Okay, so yeah. And then, which is already, I know that that's the minimum and it's not as low as that one. So I know it's not going to be the minimum. But I could also say at f of 2 and f of negative 2, that's going to be, what is it going to be? 28? I think. Okay, because 3 times 4 is 12, 12 and 16 is 28. All right, and then I need to check on the parabola. Okay, I was making sure I wasn't running out of battery. It was pushing me some sort of notification on the computer, but it was not relevant to what we're doing. Asking me to update the software. All right, so now I'm going to go and I'm going to kind of draw in that parabola, y equals x squared. Okay, so on here, we're interested in the place where y is equal to x squared, and x is also between negative 2 and 2. So I'll just plug in x squared for y, so I'll have f of x and x squared, and that will be, okay, so 3x squared plus 2y to the fourth. Wait. 2y squared is 2x to the fourth. And then negative 4y would be negative 4x squared. And so I'll just rewrite this as 2x to the 4 minus x to the 2. And okay, this is going to be something that we're going to have to actually take the derivative of and set to 0, I think. I don't know if you can see, on a factoring level, I don't know. Yeah, I think it would probably be better to just, like I could draw a sketch of this thing, but I wouldn't know where the actual extrema of that particular polynomial are. So I'm going to take the derivative and set it equal to 0 to try to find the critical points of this polynomial. Okay, so the derivative would be, 8x to the 3 minus 2x equaling 0. So I'm going to factor okay, so x is 0, or x could be, I think, a half or negative a half. All right, and so what I'm going to do is I'm going to run all of these values, and then at the place where x is 0, y is also needing to equal 0. Over here, we'll have y equal 1/4 and y again equaling 1/4. And we will run all of these through f, and we will get ourselves some sort of conclusion. But I'm going to pause the recording of this video while we do that arithmetic because, it might take a minute. All right, so after a little bit of arithmetic, which actually was not as bad as I thought it was going to be, we have determined that the absolute minimum occurred at the interior critical point. The absolute maximum occurred at the edges, actually right here. And so, that's really how it goes. It's the exact same as running the closed interval test in single variable calculus, except the checking the endpoints is a little more heavy on the algebra. But that's all I got for you.